Tonight's presentation is titled Exhaust Valve Failures. And our presenter is Mike Bush. Mike is the president of Savi Aircraft Maintenance Management. He's a CFI and also an author for numerous aviation publications, including EAA's Sport Aviation magazine. Mike is an A&P mechanic with inspection authorization privileges and was identified and honored by the FAA as the Aviation Maintenance Technician of the Year in 2008. Mike's a member of the EAA. Mike, thanks a lot for volunteering tonight to be with us to share this information. I'm going to turn control of the presentation over to you.
Good evening, everybody. Tonight's subject is exhaust valve failures, and this is an important topic because the exhaust valve is by far the most likely component in a piston aircraft engine to fail. It has the hardest job. It lives in the worst environment, and it's actually a miracle that the exhaust valves last as long as they do, and it's only by a lot of engineering magic that's possible. So tonight we're going to talk about a whole bunch of stuff centering around exhaust valves and exhaust valve failures. We'll start out talking a little bit about the anatomy of exhaust valves, how they're made, and how they fit into the cylinder system, if you will, with the guides and the springs and all of that stuff. We'll talk a little bit about the various reasons that they fail and what those failures look like, and then we'll talk about the consequences of the failures. What happens to your engine when an exhaust valve fails in flight. We'll talk a little bit about what operators can do in terms of power plant management to help prevent these failures from happening. And then, perhaps most importantly, we'll wind up talking about the ways that we have to detect exhaust valve failures at the incipient stage before they actually fail outright and impact engine performance. Because nowadays we have such good condition monitoring tools that there's really no excuse for an exhaust valve failure to happen if we're paying enough attention. So that's sort of the roadmap for what we'll be talking about this evening, and I have a lot of cool pictures of bad valves and stuff to show you as well, so it should be a lot of fun. So let's start out talking about the anatomy of exhaust valve. My background is with certificated engines, and so my knowledge is primarily centered with Continental and Lycoming engines. And there's a little bit of difference between the two, and it affects to some extent the kinds of failures that we have. And the primary difference is that Continental uses solid stem exhaust valves. And by the way, if you know anything about bore scope inspections of valves, you'll notice that this valve is in serious trouble. We'll get into that a little later, but if you'll notice up in the about the 11 o'clock position, there's a bunch of green stuff on the edge of that valve, which tells us that this valve was very close to failure, and that's presumably why it got removed from its cylinder and is sitting on a workbench here. But this is a Continental cylinder, a Continental valve rather, exhaust valve, and the Continental valves have a solid stem. In contrast, the Lycoming exhaust valves have a hollow stem, and inside the hollow is liquid metallic sodium, and the sodium sloshes around in the cavity inside the exhaust valve, and it helps conduct heat from the face of the valve, which is what's exposed to the combustion chamber, up the valve stem, where it can be dissipated through the guide and ultimately the fins on the cylinder head. So again, the difference, primary difference between Continental and Lycoming valves is that Continental uses solid stem valves, Lycoming uses hollow stem sodium-filled valves. This is an exhaust valve, a really nice cutaway showing the exhaust valve in position in a cutaway of a cylinder head. This is a Lycoming head. And with sort of the key components here, we've got the valve itself. It's pressing against a seat when it's closed, and the opening above the valve face is the exhaust port. Then we have a guide, which is the sort of the coppery colored thing that is press fit into the head. It's actually an interference fit into the head. The head is heated up and the valve guide is chilled, and then it's pressed into the head so that when the temperatures equalize, the guide is locked in place into the cylinder head. And the valve rides up and down inside the guide, and the guide is what holds it in place and holds it concentric with the seat. And then up above the valve, we have the valve spring assembly, which is what closes the valve. It's opened by a cam lobe that pushes on a push rod and a rocker arm, but then the valve is closed by a pair of concentric valve springs. So this sort of shows how it all fits together in the cylinder head. The valve, of course, is exposed to extremely high heat because it's in the face of the valve is right in the combustion chamber. So it's really important when we're analyzing how these things fail to understand how they dissipate that heat. There are basically two paths by which the heat is dissipated. The heat is some of the heat is dissipated through the contact with the seat and into the cylinder head, and some of it is dissipated by going up the valve stem and transferring through the guide to the head. So there's basically two kinds of heat transfer paths, one through the seat and one through the guide. And the Lycomings, because they have the sodium-filled hollow stem guides, they dissipate more of the heat through that stem than Continentals do, and Continentals dissipate more of the heat through the seat than Lycomings do, because they've got solid valve stems. So there's a little bit of both kinds of valves dissipate heat both ways, but the Lycomings depend a little bit more on dissipating the heat through the stem, and the Continentals depend more on dissipating the heat through the seat. Another thing before we get off of the anatomy here that it's worth understanding is the contact between the valve and the seat when the valve is closed. And if you look at that drawing that I did kind of in the lower right hand corner of the slide, it sort of emphasizes the fact that the bevel on the valve and the bevel on the seat are cut at slightly different angles, so that the contact area is small. It's the valve does not contact the seat over a large area; it's over a fairly small area. And when you inspect a valve that's been in service for a while, you should see a nice shiny ring running around the circumference of the valve, showing exactly where the valve contacted the seat. And it's sort of a black art to get this valve grinding, or the valve and seat grinding right, because if the angles are too much different, then the contact area between the valve and the seat is too small, and it doesn't provide a sufficient path for heat dissipation. But on the other hand, if the the difference in angle between the valve and the seat is too small, and the contact area is too large, then the pressure on that contact area is not as great. It's spread out over a larger area, and the valve and seat will be more likely to develop deposits on it that can cause leakage. So it's a very fine art to get this grinding exactly right, to find the best combination of heat dissipation and keeping those sealing surfaces clean. And there are a lot of cylinder shops sort of have proprietary ways of grinding this stuff and so on, but it is quite a critical feature of the whole valve architecture, and one that we don't hear talked about very much, but it's very important. One more thing before we leave the anatomy part. If the valve guide gets worn sufficiently so that the valve is fairly loose in the guide, and we'll see that the valve guide wear is one of the major causes of exhaust valve failure. But if there's enough guide wear inside the guide so that the fit between the valve stem and the guide gets sloppy, we sometimes will get a situation where hot exhaust gases that are exiting the cylinder through the exhaust port can sneak up through the annulus between the valve stem and the inside of the valve guide and get up into the rocker box area where the valve springs are, and overheat those springs and cause them to anneal and lose their springiness. So that's one failure mode that we see occasionally when the valve guides get worn excessively. At any rate, let's talk a little bit specifically about the reasons that exhaust valves fail. And there are basically three primary reasons for exhaust valve failure. One is that the valve guide and the valve seat are not machined correctly, and they aren't perfectly concentric. And this is a problem that we sometimes see, in brand new cylinders. We've seen them in cylinders that came right out of the Continental factory during a period of time. We see them in cylinders that are overhauled by cylinder shops where they don't do a proper job of ensuring that the valve guide and the valve seat are perfectly concentric. And I'll show you a picture of one of those in a minute. The second reason is that exhaust valves fail that we just talked about is that the guides get excessively worn, and the valve is no longer being held centered by the guide properly because the guide has worn. Normally the wear is sort of oval. It's more in one dimension than the other, and that's because of the mechanical action of the rocker arm that puts a side load on the valve every time it opens and closes. And the third reason that we see exhaust valve fails are where the valve starts sticking in the guide and can't close properly because of buildup of exhaust deposits on the valve stem and inside the valve guide. We see the worn guides problems a lot more in Continentals. We see valve sticking a lot more in Lycomings. And again, it has to do with the fact that the two brands of engines use somewhat different metallurgy, and the Lycomings use sodium-filled exhaust valves so that the stems absorb a whole lot more of the heat and run a lot hotter. Here's a cylinder head from the inside of the cylinder, and you can see the two where the two valves would go if they were installed. The big one, of course, is always the intake valve, and the smaller one is the exhaust valve. And you can see the end of the seats, or the the guides that have been pressed into the cylinder head. And if we take a close look here at this exhaust valve guide, notice the concentricity problem here. Notice that when this seat was ground, it's lopsided. On the left side, it's very narrow. On the right side, it's very fat. So this was a guide that was, this is a seat that wasn't ground correctly. And with a lopsided seat like this, even with a brand new valve guide, if you put the exhaust valve in there, you can't expect that it's going to seal properly all around the circumference. And so you're going to have exhaust leakage, which, as we'll see in a minute, starts the valve down the road to destruction. So this is a problem that we see occasionally with a cylinder that just came right out of the factory or right out of the cylinder shop. And so, you know, when owners have exhaust valve problems, they usually say, "What did I do wrong?" And sometimes they didn't do anything wrong. Sometimes the failure was cooked right into the cylinder when it was built or when it was overhauled. So this is an example of an improperly machined guide. Here's a case, and we see this a lot in Continental engines, where the valve guide has gotten worn, and you can see that instead of the bore inside the guide being nice and circular, it's worn oval, and it's worn that way because the valve, every time it opens and closes, has a side load on it caused by the rocker arm that's opening and closing it, and eventually the guide will oval out. It's called bell mouthing because the wear tends to be more at the bottom end of the guide than it is up at the top of the guide. But this is a seriously worn guide. The seat looks okay, but the guide clearly is worn. And with a valve in this guide, if you were looking in the cylinder with a bore scope and you rotated the prop so that you could watch the valve open and close, you would see that every time the valve closed, it would scoot a little bit sideways as it settled into the seat. And the amount that it scoots sideways is a really good indication of how badly worn the valve guide is. So we can really tell very easily when we have a worn guide just by watching the exhaust valve through a bore scope and opening and closing it a couple of times and seeing what the action of the valve is as it settles into the seat. Here's an example, and this is a Lycoming valve, of a buildup of exhaust deposits on the valve stem. This is typically caused by operating these engines quite rich, and particularly by not leaning aggressively enough during ground operations, during idle and taxi kind of operations. But when deposits build up on the valve stem, it makes it harder and harder for the valve to close because it interferes with the with the close tolerance fit between the valve stem and the seat. Now, if this happens in a Continental engine, most of the Continental engines have fairly soft valve guides. So what happens is it just wears the valve guide at an accelerated rate. But if it happens on a Lycoming, where the valve guide material is a lot harder, then typically what happens is that we get a sticking valve, one that doesn't really want to close because of all these deposits. And eventually it will reach the point where the valve springs just aren't strong enough to close the valve with all of the stuff on the valve stem, and the valve will start to leak for that reason. In Lycomings, this is a very frequent problem, particularly if they aren't leaned very, very aggressively, particularly on the ground. And normally the first symptom that we see is what's called morning sickness, where when you first start the engine, when the cylinders are cold, you'll have a cylinder that doesn't light off, and the engine is running on 5 cylinders instead of 6, or for smaller Lycomings on 3 cylinders instead of 4. And then as the cylinder head warms up and the valve guide expands because of heat, the sticking problem lessens, and the cylinder will start to produce power. So you have this situation where you've got roughness when the engine is first started, and if you had an engine monitor, you'd see that one of the cylinders was not actually making power. And then as the cylinder warms up, as the CHT comes up, the problem goes away. And this is an early warning sign of valve sticking, and it needs to be paid attention to, because if it's caught early, the problem can be resolved. But if you ignore it and it gets bad enough, you can start to get valve sticking in flight, and then we really have a problem. So morning sickness is a symptom that every aircraft owner should be sensitive to, particularly if you're flying Lycomings, because this is a problem that we see more with Lycomings than with Continentals. At any rate, once the valve starts to leak for some reason, whether it's that the seat wasn't ground correctly, whether it's that the guide got excessively worn, or whether it's that there's excessive buildup of exhaust deposits on the stem that's causing the valve to stick and not to want to close. Any of those things can cause exhaust valve leakage during the combustion events. And once a tiny leak starts to develop, and this very, very hot gas that is not supposed to be getting past the exhaust valve, because the exhaust valve is closed during this very hot part of the combustion cycle, if that gas starts leaking past the valve, it creates a hot spot on the valve wherever that leak is occurring, and it erodes metal from the valve and the seat, and it can cause the valve to warp, making it seal against the seat less effectively. So the erosion and warping will result in the leak increasing, and as the leak increases, the hot spot gets hotter. And so this is a process that once it starts, it just starts to accelerate until ultimately the valve fails. It doesn't, this is stuff that doesn't happen instantaneously. It comes on relatively slowly, and if we're really paying attention, we can detect it in various ways before it gets bad enough to cause a failure. But once you start getting leakage, once you start getting a hot spot on the valve, we call it the valve is burned. This proceeds inevitably and inexorably to a failure, unless the problem is caught and cured in time. This kind of thing is never going to get better. It's going to get worse, and it's going to get worse at an accelerated rate. It's just a real vicious cycle. So in any case, let's see, when I was at AirVenture this year, they had a nice little exhibit at the in the Continental booth where they showed a series of exhaust valves through their life from perfect all the way to failure. And they were emphasizing the fact that as the valve starts to get in trouble, the pattern of deposits on the face of the valve that can be very easily seen through a borescope telegraphs the fact that the valve is failing. And if we look at it on a periodic basis, we'll be able to detect this and not let it go to failure. And I've got a whole bunch more pictures a little bit later in the presentation, but this was one that they had up at AirVenture in the Continental booth. So let's talk about the consequences of an exhaust valve failure. If the valve does go all the way to failure, what happens to your airplane? And it depends on exactly how bad the failure is. The normal kind of failure that we see, the vast majority of the time, are failures like this. The valve on the left is a Continental valve that actually was in one of the engines on my airplane about 20 years ago, back in the bad old days before we had borescopes and engine monitors and all of that stuff that lets us detect this. And this valve failed completely. This is in the left-hand photo. And you can see that a little piece of the valve departed the premises. And of course, the cylinder compression then went to zero, and it shut down the cylinder. The one on the right-hand side is a similar failure. It failed a little bit worse, and I believe it's a Lycoming valve. But you can see in both of these cases, this is the typical kind of exhaust valve failure we have, that if the hot spot on the valve is not detected, it just gets worse and worse until finally some metal just departs the valve and it shuts down the cylinder. So most of the time, the exhaust valve failure will simply shut down one cylinder, and if you have an engine monitor, you'll see that cylinder shut down, and you'll feel that the engine is running rough because it's not running on all cylinders. And the severity of the consequences of that kind of typical failure depends on how many cylinders you've got. If you've got a six-cylinder engine, a six-cylinder engine can make, and we've actually done a bunch of tests recently down at ECI on their dynamometer, but a six-cylinder engine can make about 80% power with only 5 cylinders running. It runs rough, and it can be a frightening experience for somebody who isn't used to it. But the engine can still make plenty of power, and you can certainly make a landing at some suitable airport. 4-cylinder engines won't do nearly that well running on 3 cylinders, and we've had quite a few cases where 4-cylinder Lycomings have had a valve fail, and the result was that the airplane got put down on a road or something like that, made an off-airport landing. So if you have a 4-cylinder engine, these failures have more serious consequences than if you have a 6-cylinder engine typically. Now that's the typical kind of failure we see, but once in a while, and this doesn't happen very often, but once in a while the consequences of a failure can be worse than that. For example, if a piece breaks off of the valve, it's typically going to go out the exhaust. And if it's a turbocharged airplane, it might go through the turbocharger and take out the turbocharger. So if you're up at altitude when this happens, you might not be making 80% power in a 6-cylinder engine because you might have lost your turbocharger as collateral damage, as this chunk of exhaust valve went out the exhaust and decided to go through the turbocharger and wreck it. The worst kind of failures that I've seen, again, this doesn't happen very often, but when it does, it really gets your attention, involve failures where the head of the exhaust valve actually snaps right off the stem. And now you've got a really big thing bouncing around inside the cylinder, and it can really make a mess of that cylinder assembly. And in certain cases, if the valve gets in the right position, it can actually shatter the piston and cause a catastrophic failure of the whole engine. And here's a photograph of a very, very severe failure where the head of the valve snapped off of the stem and bounced around inside the cylinder, and you can see some of the impact marks there. And it actually took out the piston, and as a result, the entire engine suffered a catastrophic in-flight failure. So that's a worst case. We don't see that very often, but it is a possibility, and it's one of the reasons that we need to take exhaust valve condition monitoring very seriously, because we don't want that sort of thing to happen. So how can we prevent failures? Well, we can't prevent all failures, of course, and certainly failures that are caused by the cylinder not being set up correctly to begin with, we can't do anything about, at least from the cockpit. But we can do quite a bit to prevent the more common failures. To minimize the chance of exhaust valve burning, we really need to do two things. We need to keep the cylinder head temperatures reasonably cool, and we need to keep the exhaust gas as clean as possible and minimize unburned combustion byproducts that could build up on the valve stem and inside the valve guide and cause valve sticking. So those are really the two objectives that we want to keep in mind in terms of managing the power plant. And when I say keep the cylinder head temperatures cool, for Continental engines, and I've talked about this in other webinars as well, we never like to see cylinder head temperatures in Continentals get above about 400 degrees Fahrenheit, and preferably we like to keep them at 380 degrees Fahrenheit or less. And this is in legacy airplanes. And for Lycomings, the Lycomings tend to run 15 or 20 degrees hotter as a general rule in terms of cylinder head temperature, and that's partly because of the sodium-filled valves that transfer the heat to the head in a much more effective way. So in Lycomings, we like to never let the CHTs get over about 420 degrees Fahrenheit. And if we can, we'd like to keep them at or below 400 degrees. For airplanes with exceptionally efficient cooling systems, the airplanes that have been designed, basically in the 21st century, the engineering capability on these cooling systems has improved dramatically. And so if we're talking about a recently designed airplane with a very efficient cooling system like Cirruses and the Columbias and the Diamonds and stuff, those cylinder head temperatures should be kept even cooler because the cooling system is so efficient. So for those airplanes, we would subtract 20 degrees from those numbers above. And so, for example, on a Cirrus SR22 that has a Continental IO550 engine, it's rare for us to see cylinder head temperatures above 360 degrees in those engines because it's so well cooled. And similarly, the Diamonds that have Lycomings, we normally don't see cylinder head temperatures much over 380. So, and one more thing, all of these temperatures assume that the cylinder head temperature is being measured in the normal threaded boss on the underside of the cylinder head casting. If the temperature is being measured at the spark plug, and occasionally we'll see engine monitors that have spark plug gasket type CHT probes rather than ones that screw into the CHT well on the bottom of the cylinder. If you're measuring it at the spark plug, it typically runs about 40 degrees hotter. So a spark plug gasket probe that's reading, 420 degrees, that's really equivalent to 380 roughly if it was being measured in the standard place. So that's talking a little bit about our objectives in keeping cylinder head temperatures cool. And the other objective we had was to keep the exhaust clean to minimize the amount of deposit buildup on the exhaust valve stems and inside the exhaust valve guides. And to do that, we want to operate the engine aggressively lean, preferably lean a peak, at all times other than when we first start the engine cold and when we're making a full power takeoff. Obviously, during those two times, when we first start the engine cold and when we're making a full power takeoff, we need to use a full rich mixture. But all the rest of the time, we want to lean the engine aggressively, and it's especially important that aggressive leaning be done during all ground operations, including idle and taxi and run up, because it's during ground operations that we get a lot of the buildup problems on these engines. In a leaning webinar that I did that's on the EAA server, I talked at length about an experience that they had at Embry-Riddle's gigantic flight school down in Florida, where they were just having all sorts of problems with these Lycoming engines in their Cessna 172 fleet, until Lycoming and Cessna went down there and started investigating and said, hey, you guys have to lean these engines a lot more aggressively. And once they started doing that, their problems went away. It's really important to lean these things aggressively. Using these techniques, I was able to take the Continental TSI 0520 engines, my Cessna 310, to well over 200% of TBO with absolutely no exhaust valve problems. I've actually changed 3 cylinders on that airplane in its life, and they were all changed because of cylinder head cracks, not because of exhaust valve problems. I've had a perfect batting average with exhaust valves on those things. So some real attention to detail in how you operate these engines, and mainly compulsive attention to cylinder head temperatures, and also leaning them aggressively will pay big benefits in terms of minimizing this sort of problem. So finally, let's talk a little bit about how we detect incipient valve failures before they happen. And as I said, back in the bad old days, we used to see valve failures on a fairly regular basis. But today, with the tools that we currently have, and primarily the borescope and the digital engine monitor, there's really no excuse for these valves going to failure, because we can detect the failures with quite a bit of lead time before the incipient failures before they actually fail hard. And so the 2 major tools that we have are borescope inspections and engine monitor data analysis. Well, let's just quickly look at both of those. This is a photo of my friend Adrian Eichhorn, who's an ANPIA and a Bonanza guru back in Manassas, Virginia, and he's using his very nice borescope setup to borescope the exhaust valves on a Bonanza here, and you can see that he's looking at the images on a big TV screen here. And if we blow it up a little bit, you'll see that with the borescope we can get just an extraordinary amount of detail on exactly what the valves look like. We can look at the exhaust deposit pattern on the face of the valves, which is probably the most important thing that tells us whether the valve has developed a hot spot. And by opening the valve, we can look down and see the stem and the end of the guide and a good part of the seat. So with borescopes nowadays, we can really inspect these things in great detail, and it's very easy to do. Now, Adrian is using a very elaborate setup that he uses, actually a medical endoscope. It's probably about $10,000 worth of equipment, but you don't need to do that. Nowadays we've got really excellent borescopes. This is the SnapOn BK8000, which is the one that I'm recommending nowadays. It's about $1,000, and it's really quite an extraordinary thing. It's just got a ton of features. It has excellent lighting. It has excellent image quality. It captures digital still images. It captures movies, so that you can actually take a movie of the valve as it opens and closes. It's really an extraordinary device. One of the problems that we have in terms of borescope inspections is that mechanics really haven't received any training in how to do borescopy, since we've really only been doing them now on piston engines for the last 10 or 11 years or so. And so most A&Ps have never been taught how to do a borescope inspection or what to look for. And Adrian got a grant from the AOPA Safety Foundation to develop this training aid that it's a big wall poster, and it has a bunch of really good images of what good valves and bad valves look like and what to look for. And you can actually download it right off the AOPA website. If you just Google anatomy of a valve failure, it'll take you right to it. That's the title of the poster. And also, I think you can call them up and they'll send you the actual big glossy wall size poster for free. You might want to get 2 of them and give one to your A&P. But it's a really, really great training aid for mechanics in terms of what to look for and what not to look for. It talks about the color patterns that we see on the face of the valve, and how the color pattern really gives us a kind of a temperature map, so that, for example, that number 1 valve, the pattern looks pretty symmetrical, which means that the valve is running about the same temperature all around its circumference. If you look down at say the number 4 valve, you see extreme asymmetry, where the valve is running very, very, very hot up at the 12 o'clock position, and it's clearly developed a hot spot. And then as you progress towards picture 5 and 6, you can see the worse and worse hotspots. Adrian has got a library of literally hundreds and hundreds of valve photos, and we sorted through them to get some good ones. Some of these are interesting. These valves are all in very good condition. You can see how different they look, but they all are symmetrical, and they're all in good condition. It's the symmetry that tells you that we don't have a hotspot developing. But the reason for the very, very different appearances here are that these engines were operated in different ways. I mean, for example, the one on the right there has extremely thick deposits, and it's caused by that engine was operated quite rich. And those are the kinds of deposits that if they build up on the face of the valve, they don't really cause a problem. But when those same deposits start building up on the valve stem, that's when we start getting problems with stuck valves. So it's really important to minimize the deposit buildup by running the engines lean. So again, this poster called Anatomy of an Exhaust Valve Failure is really a terrific thing, and you can download it off the AOPA website. If you just Google Anatomy of Exhaust Valve Failure, you'll go right to it, and it's a really cool thing. The other tool we have besides borescopy is engine monitor data analysis. And we discovered that most of the time when an exhaust valve develops a hot spot, you can see it as a slow rhythmic oscillation in the EGT. Here's a really good example of one where this yellow trace, which was cylinder number 3, is a 6-cylinder engine, and cylinder number 3, the exhaust valve has developed a problem, and you can see how its EGT is oscillating. Here's a close-up of that, and you can see that cylinder number 3's EGT doesn't look like any of the other 5 EGTs. It's got this slow, very, very rhythmic oscillation, and if you look at it, it's oscillating up and down right around 1 cycle per minute. So it's quite slow, but it's very, very regular, and it's and a pattern like that almost always means that the exhaust valve has developed a hot spot. And here's another very extreme one that we got. We isolated just that one EGT on this one, but you can see the oscillation, you can see the regularity of it, and so on. But when we see something like this in the engine monitor data, that is indicative of a valve that's developed a hot spot and is beginning to burn. It doesn't. Not every exhaust valve failure does this. The reason for the oscillation is because the exhaust valves in these engines, in Continental and Lycoming engines, have what's called a rotator cap on them, and the rotator cap rotates the valve a small fraction of a degree, I think maybe 1/3 of a degree, every time the valve opens and closes. And because the valve opens and closes something like 2,400 times a minute or something when the engine is running, the valve winds up turning about 1 revolution per minute roughly at cruise RPM. And so if the valve has a hot spot, that hot spot will rotate around with the valve, and it will move to hotter parts of the combustion chamber and then to cooler parts in a cyclical fashion, and that will be reflected by this slow rhythmic oscillation of exhaust gas temperature. Now, as I said, this doesn't work on this doesn't predict every exhaust valve failure, because if the exhaust valve fails because the valve is sticking, it may stop rotating, and if it's not rotating, of course, we can't see it with an engine monitor. But other than the case of valves that fail because they're sticking, this is a very good predictor of exhaust valve failure. And the borescope is the gold standard, but engines typically don't get borescoped except maybe once a year if you're lucky, and a lot of shops don't even borescope them at all. The engine monitor, I would guess 50% of the GA fleet are equipped with an engine monitor, and it's watching 100% of the time. So we think this is a real important tool. It's usually difficult to detect this in the cockpit. It's usually because the oscillation is so subtle and so slow that you normally wouldn't notice it. It's a lot easier to detect it by dumping the data on a regular basis and analyzing it. As I've talked about before, we have a website where you can upload engine monitor data. It's called SaviAnalysis.com, and there's a whole bunch of tools there that you can use to graph it out and so on. And it's free, or you can sign up for our pro service and have a professional analyze it for you. But we've got I don't remember, close to 5,000 aircraft owners are uploading their data to this site, and we've got 500,000 flights that have been uploaded now since we launched this thing about 2 years ago. So one of the things that we spent quite a bit of time working on, and we rolled out, announced it at AirVenture, is a software enhancement called that we call FEVA, Failing Exhaust Valve Analytics, and it's a software algorithm that every time data gets uploaded to the Savi Analysis system, it it examines the EGTs looking for this kind of this oscillation pattern, and if it sees it, the software automatically generates an alert. When we get that alert, one of our analysts takes a look at the data and it confirms that it's not a false alarm, and if so, we notify the aircraft owner that his data seems to indicate a failing exhaust valve in the number 3 cylinder, whatever it is, and recommends that he go get that cylinder bore scoped at the earliest opportunity, because there's a good chance that that valve is in the process of failing. Now, we would never recommend removing a cylinder based solely on EGT oscillations. We always ask that the valve be bore scoped to confirm the diagnosis, because a bore scope is the gold standard. The problem is that mechanics haven't really been trained to bore scope cylinders. I mean, to me, anytime this top spark plug is out, you ought to stick a bore scope in and look around. But very few mechanics do that, and most shops won't even try to bore scope a cylinder unless it has low compression or something. And there's still a lot of shops that don't even own a bore scope. So we think that using engine monitor data as a backup is an important thing. But between bore scope inspections and watching the EGT for these oscillations, there's really no excuse for an exhaust valve to fail outright anymore. It's a detectable situation, and with conscientious engine monitoring, we can prevent these failures from happening. Tim, that's all of the prepared material I have. I think we could open it up for some questions.
Fantastic, Mike.
What do we have, about 20 minutes or so?
About a half an hour, actually. It's 9 o'clock, so we got a half an hour.
Okay, I'm game.
Okay, let's see here. Let's dig right into them. Craig's got a question here. Can exhaust valves be reconditioned, reground, or should valves be replaced with new?
Normally, valves are replaced with new. There's really not a procedure for overhauling them or restoring them. Now, occasionally, if a leak is caught very, very early, and it is occasionally possible to actually use a little valve grinding compound and sort of hone the valve to seat interface without removing the cylinder. You normally have to drop the exhaust and then work through the exhaust port and then flush the grinding compound out, obviously, before you put everything back together. You need to remove the rocker arms and the valve springs, and then you can hone the valve in place. And we've had pretty good success doing that if the problem is caught really, really early. But if the hotspot has gotten to the point where it's showing up as a lopsided pattern on the bore scope, which means that there's metallurgical damage to the valve, normally the valve is simply replaced with a new one, and the seat may have to. I mean, both the seat and the guide. Usually the guide is replaced. The seat is often just reground in place. And this is the sort of thing that you send the cylinder off to a cylinder shop to have done. But no, we really can't. There's no procedure for overhauling exhaust valves. When they start to burn, we have to replace them. The continental valves aren't that expensive. The Lycoming valves are a little bit more expensive because they're sodium filled. They're a little more exotic.
A couple of questions here from folks about the rope trick. Wondering if it's okay to use the rope trick to try and break that non-seating exhaust valve.
Well, yeah. Again, if this is something that we do primarily with Lycoming engines, if if the valve starts to stick, I mean, for example, if the engine starts exhibiting morning sickness, the mechanic will pull the rocker cover, pull the rocker arm, and the valve springs off, and then do what's called a wobble test. And there's a Lycoming service bulletin that talks about how to do that, where it checks to see how much you can wobble a valve in the guide. And if there's very, very little wobble, it means that the valve is too tight in the guide. And there's this procedure, which is generally referred to as a rope trick, that allows you to drop the exhaust valve out of the guide into the cylinder, use a reamer to ream out the valve guide and get the buildup of deposits off of it, and then work the valve back into position without removing the cylinder. Again, this is something that you do as a remedy to a sticking valve problem. It's not going to solve a problem where the valve has developed a hot spot and has metal erosion on the valve itself. But if the problem is simply a matter of getting rid of deposits, that can sometimes be done without pulling the cylinder, but by dropping the valve into the cylinder, reaming out the guide, and then using some mechanic's fingers metal tool through the spark plug hole to work the valve back into the guide, and then reinstall the springs and so on. So that's the deal on the rope trick, and it is something that we do on a regular basis, mostly on Lycomings and typically when the engine starts to develop this morning sickness symptom.
Jose's wondering if valves also fail due to cupping, so that they can't seal anymore.
Have not seen that a lot. It's a theoretical possibility if things get really, really hot, but it's not a failure mode, at least that I've encountered in the 500 and some odd airplanes that we manage. So I would say it's not a common failure mode in these engines.
Donald's wondering, do roller rockers reduce guide wear?
No, roller rockers would have nothing to... Oh, roller rockers.
Yeah.
Okay. I was thinking roller tappets, because to the best of my knowledge, there are no approved roller rockers in certified engines, and there may be some, in experimental engines, but that's not an area that I have experience with. Obviously, the purpose of a roller rocker is to eliminate a lot of the side load that a conventional rocker puts onto the valve stem, and to reduce valve guide wear that way. There actually was an STC roller rocker arm for Continentals, must have been 20 years ago. They got an STC, a bunch of people installed them, they started to fail. The FAA basically AD'd them out of existence, and nobody's ever tried that again. So at least in the certified world, to my knowledge, there are no engines with roller rockers. I don't have any experience with them. There may be some in the experimental world, but I can't, because that's not the area I practice in. I really can't comment on how successful they've been, other than that in theory. I mean, that the whole theory is that they should minimize side loads on the valves, and thereby minimize the kind of oblong or elliptical guide wear that I sort of showed you in that picture. But as I said, it was tried once on Continental engines. It didn't work out. Apparently the things had failures, and the FAA basically AD'd them out of existence, and that was the end of that experiment.
Bob's wondering, what are the valve stem deposits made of? Carbon, lead, or something else?
You know, that's a really good question, and I can't tell you exactly what they're made of. I could probably consult with some people who know that better than I do and get an answer. If you want to drop me an email, I could try to get an answer. I think certainly part of the deposits are lead deposits that would probably not be present if we were running unleaded avgas, and at some point in the future, obviously, we will be running unleaded avgas. That may help the deposit picture. But you know, I can't tell you exactly what the chemical composition of these deposits are, other than I know it's really hard, really nasty stuff, because I've run my fingernails over a bunch of these valves that have been crudded up, and this stuff is very, very hard. It's not something you can scrape off very easily. The deposits adhere very, very firmly to the valve stem and are hard to dislodge. But it's a very good question, exactly what they're composed of, and drop me an email. I'll try to get an answer for you.
Great. Stephen asks, is coloring of valve failure dependent on the type of fuel used?
Would you say that again?
Is the coloring of the valve failures dependent on the type of fuel used? So is there a different color failure if it's 100 low lead versus auto?
It's like, is the color pattern dependent on the fuel used?
I think that's the question, yes.
You know, honestly, I can't answer that, because virtually all of the engines that we deal with are running on 100 low lead right now. I'm not aware that any of the airplanes we manage are running on auto gas, and so I don't know the answer to that. I would certainly expect, because at least some component of the deposit is lead, that would change significantly if the engine was running on unleaded fuel. But I don't really have any experience with that, so I don't know firsthand what that would look like.
Okay. Robert's wondering if using additives to the oil would help eliminate the carbon buildup.
No. No, there's nothing. There aren't any additives that you can use to prevent that. And the reason that there aren't is because there's really no way for those additives to. I mean, if the buildup is due to lead, you can add TCP to the fuel, tricresyl phosphate, as an additional lead scavenging agent, and there is a lead scavenging agent already built into avgas called ethylene dibromide. Some operators add TCP, tricresyl phosphate, to the fuel as an additional scavenging agent. But in my experience, if the addition of TCP is really not necessary if the pilots are taught to lean correctly. If you're leaning the engines aggressively, particularly during ground operations, then the lead will be well scavenged by the scavenging agents already in the fuel, and you don't really need to add anything to the fuel beyond what comes out of the pump. But TCP is an available lead scavenging agent that's sold commercially, and it's FAA approved, and you can put it in your fuel if you want to. Alcor sells it.
Rich is wondering if you have a second recommendation for a bore scope, maybe at a lesser price than the SnapOn one.
You know, I've never found a a borescope that's significantly less than $1,000 that provides decent quality. And I've tried a lot of stuff. The best you can do in that area is there is a pretty thriving business in reconditioned dental intraoral cameras. And in fact, I've got one that I use in my hangar that I picked up off of eBay for about $700, and I've heard of people finding them for less than that. I've heard of people finding them for $500 or so, and they do a very good job of imaging. But in terms of buying a new one, I don't know of a new under $1,000 borescope that provides decent images, and I've looked for that for a long time because obviously we'd like to see that. One thing about, say, the BK8000 or something like that, it would be a really great thing for, say, an EAA chapter to buy. Because you only use it a couple of times a year, and it would be a great thing for a bunch of people on an airport to be able to share. You know, because if you got 10 or 15 guys to go in on it, then the cost would be to each of them would be fairly minimal. But you know, the direct answer is no. I'm not aware of any borescope significantly less than $1,000 that I could recommend, at least not a new one.
Okay, Thomas wonders how frequently or approximately after how many hours should we do a borescope and dump the engine monitor data?
Well, as I said, in my opinion, the cylinder should be borescoped any time the top spark plug is removed, and that typically means certainly at every annual inspection, because the plugs are always removed at annual, and normally for airplanes that fly a lot, the spark plugs normally have to come out for cleaning and gapping and stuff about every 100 hours. And any time the spark plugs are out, to me, it's just it would just be a crime not to stick a borescope in the hole and look around. It only, you know, adds 20 or 30 minutes to the whole process, and it's very worthwhile. So I would recommend borescoping the cylinders every 1 year or 100 hours, whichever comes first. And basically, any time the top spark plugs are removed, that's the time to do it. And the other question was dumping engine monitor data. We recommend to our Savi Analysis clients that they dump and upload the data at least 3 times a year. The more the better. One of the things that we would really like to see happen, and I think we're on our way towards it, and it probably won't be many years before we have this capability, would be engine monitors that automatically transmit their data to a server, say like Savi Analysis, literally every time at the end of every flight. That they just connect to the internet via Wi-Fi or via cellular modem or something, and transmit the data in, so that the pilot doesn't have to do anything, and that the stuff is updated continuously. But we don't have that now. We don't have the ET call home capability in the engine monitors yet, and so as things presently stand, I would recommend doing it at least 3 times a year, dumping the data and uploading it, taking a look at it, you know, passing it through our FIVA algorithm that automatically looks for that oscillation pattern and alerts on it. So 3 times a year, I would say, it would be a good recommendation for that, Tim.
Okay, great. And Paul John's just wondering, does the power level affect the possibility of burning a valve?
Well, only to the extent that it tends to affect cylinder head temperature. But if you keep the cylinder head temperatures at or below the targets that I was talking about, you should be fine.
A follow-up kind of on that same thought then is,
Yep.
Jesus wonders, how long does it take to burn the valve in something like a Cirrus SR22 with CHTs over 380 to 400?
Well, first of all, in the Cirrus SR22, we very seldom see CHTs that high just because the things are cooled extremely well. But I think really the question that he's answering, or he's asking for, is how long before a valve actually fails can we detect that it's in trouble using the borescope and the engine monitor. And you know, we haven't yet done a rigorous study of that, so I can't give you really good numbers. I can just give you my general impression, and my general impression is that that we can normally detect exhaust valve distress on the order of 100 hours before the valve would actually fail and shed a piece of metal. Again, I wish I had a really good study to provide data from. I don't, so I'm sort of giving you this as more of my impression than as a result of any kind of a rigorous scientific study. But in general, I would say that we normally can detect an exhaust valve that's getting into trouble on the order of 100 hours before it would actually fail outright.
Okay, and
don't hold me to that, but that's my impression.
Okay, Merlin's just wondering, running lean increases EGT. Does this have any effect on valve failure?
Well, of course, that's not a true statement. So, running lean does not increase EGT. Running, as you lean, EGT gets higher until you get to a peak at stoichiometric, and then as you continue to lean on the lean side of peak, EGT comes back down again. So to say that leaning aggressively increases EGT is just not a true statement. It increases it, and then it decreases it again. And I'm certainly not recommending running engines at peak EGT. I recommend running engines, and the way I run mine is to run them lean at peak almost all the time.
Okay. Just to follow up here then from Mike, he's wondering if you can just discuss a little bit the relationship of percent engine power, EGT, and RPM during lean of peak operation and its relation to exhaust valve failure.
To be honest, that's a complicated subject that I don't really feel comfortable trying to address without I've gone into that in detail in some other webinars where we specifically talked about leaning and stuff, and it's a little hard to just do it off the cuff. There is definitely a relationship. For example, as you reduce RPM, EGTs go down, because as you reduce RPM, you increase the time between the time ignition happens and the time the exhaust valve starts to open, so that there's more time for the the exhaust gas to cool before the valve opens and so on. That, in my view, that EGT is not the primary determinant of exhaust valve failure. So I sort of hesitate to get too deeply into that subject tonight, Jim.
Okay.
I mean, it's a complicated subject, and
yeah, sure. Oh yeah. Victor's just wondering, is cylinder head temp directly related to baffling more so than leaning?
well, it's a combination of the two. If cylinder head temperature is excessive, there are really two reasons that it might be excessive, and one is that the cylinder isn't leaned appropriately, and the other is that it doesn't have enough cooling air. And it's very easy to determine which is the cause, because if we run a cylinder rich a peak and we run it lean a peak, and it stays hot both rich and lean, then we know that the problem isn't a fuel flow problem. We know it has to be cooling air. On the other hand, if the cylinder runs, hot rich a peak and cool lean a peak or something like that, or vice versa, then we know it's a mixture related problem. So it's easy to determine which it is by doing a test flight, but cylinder head temperature is really a function of both of those things. It's a function of how much heat is being generated in the cylinder during the combustion process, and how effectively that heat is being removed through air cooling.
Larry's wondering, would an engine analyzer indicate a potential problem with a solid stem valve that does not have the rotator caps?
No, it wouldn't, but I'm not aware of at least in any certificated aircraft engines that don't have rotator caps on the exhaust valve.
Okay.
I mean, he may be referring to some experimental engine, and I can't tell you whether, say, a Jabiru has rotator caps, because I've never worked on one, but certainly Lycomings and Continentals have rotator caps.
Justin's wondering if you know anything about how they the fabrication process for the Lycoming valves to get the sodium into the valves.
I don't know that. That would be a very interesting thing to see how they're made. And I have visited the Lycoming factory, but they don't do it there. There's a subcontractor who makes those valves for them. So I honestly don't know how they do it, but it's probably very tricky, because metallic liquid sodium is nasty stuff.
Roger's just wondering if you've had any experience with the new Lycoming roller tappets, and have they really solved any problems?
I haven't. I don't think they've been out long enough to really know. But on the other hand, I haven't heard any bad things. I haven't heard any cases of the roller tappets coming apart or anything like that, which is, of course, what you worry about when you introduce a roller tappet. It's got a moving part that a solid one doesn't have, so you worry about whether it might fail. And I haven't heard of any cases of the roller tappets failing. I mean, that's why the roller rocker arms got AD'd out of existence, because they started breaking. But I've not heard of any cases yet with the roller tappet engines coming apart. But they haven't been in the field all that long, and so I'm not sure that we have seen any engines with roller tappets that have gone all the way to 2,000 hours or something to know exactly what effect it would have in terms of longevity. It's a little early to answer that question.
Okay, Darren's wondering if you've heard of any valve failures due to failed hydraulic tappets, maybe with excess clearance.
No, to be honest, I haven't. I mean, we've seen that happen. We've seen these engines develop audible valve clatter because the lifters aren't pumping up. But I've never actually seen a valve failure caused by that. Might have happened, but it certainly is not on my radar screen.
Gotcha. Let's see. Daryl's just wondering, the CHT temps that you gave as maximum, wondering if you can put that slide back up to share with people. And also, is that for all phases of flight or just the cruise?
Well, it's really for all phases of flight as far as I'm concerned. Let me see if I can find the slide for you guys just a minute. That was the slide, I think. And again, those keep in mind, those temperatures are not the manufacturer's limits or anything. Continentals typically have a CHT red line of 460 degrees, and Lycomings have a red line of 500 degrees. But those are sort of emergency numbers, and we certainly don't want to be running cylinder head temperatures anywhere close to those red line values. So these are my recommendations as to, and they're purely mine. They're not official in any way, but my recommendations about where we would like to try to keep CHTs, and it applies to all phases of flight. And again, usually the worst case CHTs occur during the initial part of the climb. That's normally where we see high CHTs. And in the Savi Analysis platform, when you set up your airplane in there, one of the parameters that you can set is where you would like the high CHT alarm in the platform to go off. And so if you set it, say, at 400 degrees, then any flight that you upload that has a CHT over 400 degrees, any point in the flight, will be flagged as a high CHT flight. And when you actually graph it, there'll be a red line at 400 degrees that kind of shows you where that red line is when you're looking at the graph, and you can set that to whatever the value you want it to be that's appropriate for the particular aircraft.
Great. We're getting close to the end here. Let's see if we can get another question in here. Roger's just wondering, does the valve seat get damaged or have signature signs of damage when a valve develops a hot spot?
The seat can get damaged, but normally most of the time it's not damaged enough that it can't simply be repaired in place. I guess theoretically there could be cases where it would be damaged enough that you'd have to install a new seat, but I think that happens only very rarely. I think most of the time the seat can just be dressed and remain in the cylinder head.
Gotcha.
Normally the guide gets replaced and the valve gets replaced.
Okay. Last question then here. Gary's just wondering, would a failing exhaust valve also show itself through pre-ignition tendencies?
It's a possibility that it is possible that an exhaust valve, when it's right at the very point where it's going to fail, the hot spot could get hot enough that it would start glowing and causing pre-ignition. I'm not aware that I've ever seen that happen, but I know it's a theoretical possibility. Pre-ignition events tend to be so violent that they tend to destroy most of the forensic evidence, and after the pre-ignition event there's molten aluminum all over the place, and it can be really hard to figure out exactly what it was that got hot enough to cause pre-ignition, just because the pre-ignition event is so violent that it sort of destroys the crime scene.
Oh, well, that was a great webinar, Mike. Very interesting. Thank you so much for that. Any
Thanks.
closing comments you'd like to make to the audience?
Well, just a reminder of the upcoming webinars. In November, we're going to be talking about mechanics liability, getting a little bit into some of the legal stuff that make mechanics nervous. And the reason that's an interesting subject is because a lot of decisions that mechanics make are driven by their concern about liability. So it's really important for aircraft owners to understand how mechanics think about this stuff and what owners can do to make them less nervous. So we're going to be talking about all of that kind of stuff in November. December, we'll be talking about the perils of cylinder work and why replacing cylinders in the field, particularly multiple cylinders at once, and particularly things like top overhauls, is risky business and have caused a lot of catastrophic engine failures as a result of the maintenance, and talk about what steps we can take when we do have to do cylinder work to minimize the risk. And then the January one will be talking about how we diagnose rough engine problems. And so those are the next 3 webinars coming up. All subjects I think will be pretty interesting. And just finally, we put out a monthly newsletter, and you can sign up for it. It's an e-newsletter, email to you. You can sign up for it either on the SaviAviator.com website, or I think there's a checkbox in the survey that people can check and sign up for the webinar. And finally, I'll remind you that my book is on Amazon if you're interested in it. It's still the #1 seller in aviation maintenance on Amazon, and they're selling it for about $12 now. So if you're interested, it's a pretty interesting book, and it's gotten some good reviews. So Tim, I think that's about all I have, and we'll do this again in a month.
Oh, that sounds great, Mike. Yes, we will. A number of comments from the attendees tonight thanking you so much for the great webinar, and comment here from Eric. Mike's book is awesome. Just buy it. So there you go, another positive review. Thank you so much, Mike, for coming on board with us tonight and continuing your series of webinars and savvy aircraft maintenance. It's sure a pleasure to be on this end and working with you, and having kind of a ringside seat to listen to you. It sure is educational, to say the least. So thank you so much. I really appreciate it.
What have we done? Something like, I don't know, 40 some out of these now?
It's something like that.
We've got quite an archive.
It's a treasure chest. It really is. There's a lot of good information there for everybody still listening. We got about 400 people still listening. The EAA archive has a video for each one of these in the past, so they're all online on the EAA website, where you can go back and refer to. I know there was a lot of discussion tonight about leaning and lean of peak operations, and you've done a couple different webinars on those in the past that
I think we've done a couple of webinars on leaning specifically.
Mm-hmm.
Hopefully you'll be able to edit out the little false start we had at the beginning.
Yeah, we'll be able to do our little magic on that.
Good.
Very good, sir. Thank you so much. You have a great night. To all the attendees, have a great night. Good night, everybody.
Good night, everybody. Thanks for coming.